Hello everyone, this is Aobo homework 10. So let's see the first questions. Here are my understandings about this process. The first is Poisson process. We can find that for Poisson process, that x0 is equal to 0 and xt1 minus xt2 is equal to the number of calls received in T1, T2, T1. So with this one like this, so we can easily find that its probability mass function is this, and the mean of the Poisson process is like this, and the autocorrelations is RT1 T2 is lambda squares and times T1 T2 and plus lambda minimum of T1 T2. That is my understanding of the Poisson process. So as for the Poisson increments, so the Poisson increments is that with xt is a Poisson process and defined above, and sigma is more than 0, is more or equal to 0, and it is given like constant. We construct a new process, so we can easily find that xt is equal to sigma of the xt plus sigma minus x of t. So we can get that the probability of the mass functions of this Poisson increment is this, and the mean is this, and the autocorrelation is like this. And for the third question, so the Poisson impulse, we define that a statistics process z of t as the following. That is, z of t is equal to differential of xt of dt. That is the limit from limit of sigma more than 0 and y of t. So that the mean of this is equal to lambda, and autocorrelation is like this. So that is for the Poisson increment. And for the semi-random telegraph signal, the semi-graph random telegraph signal, the statistics process is defined as the following. That is, x of t is equal to 1 and is equal to minus 1 for k is even or k is odd. So we can easily define then the probability mass functions of this semi-random telephone signal is like this, and the mean is e of minus 2 lambda t, and autocorrelation is rt1 t2 is equal to e of minus 2 lambda, and t1 minus t2 is construct. So for the fifth question, the random telegraph signal is at late a, maybe a random variable of independent of x of t. So with a p of a equal to 1 equal to p of a equal to minus 1 is equal to 1/2. So that is form a new process. Yt is equal to a of xt. Then Yt is a random telephone signal, and its probability mass function, mean, and autocorrelation is like this, and this one. So the sixth one, the random walk. The random walk's probability mass function is like this, and we can easily define that is from the book, from the lecture notes, and the mean is equal to 0 because the random walk is even function, and the autocorrelation is like this. It's a minimum of n and m as s squares. So the last one, the Wiener process. We define the Wiener process as a limited process of random walk. A limited process of random walk. That is, Wt is equal to limited x of t s from infinity to 0 and t from infinity to 0 and n to the infinity. So the probability density function, and we can easily find that is like this, and the mean is like this. So the autocorrelation rt1 t2 is like this. Okay, so let's see the second question. So my understandings of these properties for the first one is a wild statistic process. That is, e of xt is equal to eta and equal to a constant. That is this one. And for the second one, independent increment process. That is, x of t is a process with independent increment if a p of xt to ta minus xtb is less or equal to x of c. That is, when x of tc minus xtd is less or equal to x of 2. So that is equal to this. So for any non-over damping increment is we can easily define that the independent increment process is like this. So the third one, the Markov process. The Markov process is that a process x of t is a Markov process if the past has no influence on the statistics of the future under the condition that the present is known. That is a Markov process. That is for any n and t1 more than t2 more than tn. So we have p of this one is equal to xt and x of t3 is equal to t3, and that is equal to p of xt1 less and equal to x of t1, and conditional probability of xt2 is equal to xt2. So for the fourth question, the normal process. The normal process is a process and xt is said to be normal if the random variable f x of t1, x of t2 from x of tn are jointly normal for any n and any t1 to tn. So that we can easily find the fx of double is like this, and where x is equal to this and x is equal to and is like this. So the fifth, the strict sense statistic process. We see that a real statistic process xt of t is stationary in strict sense if its statistics is not affected by a shift on the time axis. So that means we can easily find that for this fifth condition, x of t is as if and only if the fx of this double integral and is equal to fx of this one for any n and any t1 to tn and any sigma. And xt is SSS for f, and that means fxxt is equal to fxx, and e of xt is equal to eta equal to constant, and fx the double integral is equal to fx the double integral. That is t1 t2 is equal to t1 minus t2. And the last is rt1 t2 is equal to rt1 minus t2 if e of x squares t of t is exact. So if it's exact, we can get that. So the sixth one is white noise. As for the lecture notes, white noise, that is v of t is a white noise if RVV is t1 t2 is equal to qt1 and delta t1 minus t2 from the lecture notes. And the seventh one is the mean algebraic process. The mean algebraic process is a very funny process, and we can easily find that if this limit is equal to e of x of t in mean square sense, then we can easily find that the limit of the xt must be a constant. For example, e of xt is equal to eta. So xt is a mean algebraic free if and only if limit of x is equal to 0. That is a mean algebraic process. So the last one, the martingales. Oh, I'm sorry. So the mean algebraic process, we have the sufficient conditions. The sufficient condition, that means if x of t is WSS, and we can get that this and xt is a mean algebraic, and if xt is WSS and limit then we can get that this one is a mean algebraic. Yeah, so the last one, okay, that it is.